Right, I hope you are back with some freshly washed hands and that you are remembering to clean your devices as well. Some of that sanitizer, some of that soap, making sure that you're washing off. I know that most of you spend most of your day on your smartphones or tablets or a computer. Just make sure that you are cleaning those keys, cleaning those screens with some sanitizer or some soap. Okay, so before the break, we took a look at what is a polar molecule. Okay, well, first of all, we need to decide if something is polar because that decides the type of intermolecular forces. There are two requirements for something to be polar, and we took a look at the first one. We need to have polar bonds. Now, polar bonds are when you've got this change in electronegativity, which is, some people say it's an END, electronegativity difference, is equal to, let's say, a range of 0.4 up to 1.4. Now, it depends on your textbook and how you've been taught because these ranges do vary. Anything above 0 is slightly polar. And the higher that number, the more polar the bond. And what that makes is actually called a dipole moment. Okay, so a dipole moment is a pull on those electrons. It's an electron pull. The higher this number, the higher the pull towards the one side. Then the second thing is that for a molecule to be polar is we need to have a vector sum. Now, please don't be scared because I said the word vector. This has got nothing to do with the physics that you've been doing with Newton. That's a separate paper. So vector sum of dipoles. Now, that doesn't make any sense to anyone until you actually explain it. So please don't panic. I'm just going to neaten up my writing because some of you are taking some notes. So vector sum of dipoles, that means, quite simply put, is that the dipoles add up to something other than 0. So you cannot have these opposing forces. Now let me just remind you what a resultant is when you've got forces pointing at each other and they're the same strength, they're going to add up to 0. Or if they're pointed in opposite directions, they're going to add up to 0. So what I want to do is just run through a very simple example with you and just show you what I mean in terms of a vector sum of dipoles. Okay, so now I hope that you've got a periodic table with the same figures as I do. Here we go. What we're going to do is we're going to do two molecules together. Okay, the first molecule which I'm going to look at is CO2. So carbon dioxide. Now, I cannot tell by looking at that formula if this thing is polar or not. I need to have it drawn out in the correct shape. So carbon and BSEPR, the shape of molecules, tells me that carbon dioxide is a straight molecule. So I've got carbon on the one side, I've got oxygen on the left-hand side and on the right-hand side surrounding it. So there we go. We've got carbon and oxygen bonding to each other. Just going to swap colors to show you what I'm doing in terms of electronegativity. So carbon has got a number of 2.5 on the Pauling scale, oxygen of 3.5. So we've met the first requirement. We do have a difference between the two. This is definitely a polar bond. So there's a pull on electrons towards the oxygen. The one with a higher number is going to win the fight with those electrons. So very important to be able to accurately read this off the table and just make sure that we're getting those correct numbers. So carbon and oxygen are fighting for electrons. Oxygen on either side is going to be winning, but here's the thing. If there's a tug of war in two directions and they're both pulling exactly the same strength, so I've got carbon, oxygen, carbon, oxygen. Here we go. Right, I've got a pull on this side of, we can actually calculate this. I think it's 1.0. There we go. So 3.5 minus 2.5. Now you do this individually for both. You go 3.5 minus 2.5. There's a difference of 1.0. But if I drew a free body diagram of two things pulling equally in opposite directions, you know from grade 11 science that these two things are going to cancel out. So for the first check, I've got polar bonds, definitely. So that's the first requirement. But there is a zero sum of dipoles. Now that means that these dipoles have added up to naught. So if I've got a zero sum of dipoles, that means that this molecule is nonpolar. So therefore, CO2 is nonpolar. Now, we still haven't decided what's going on in terms of intermolecular forces. It's not something that we've done yet. But deciding if a molecule is polar or not is really, really important. It's in fact the first thing, because you can tell immediately if two things are going to mix. Like oil and water don't mix, because water is polar and oil is nonpolar. That's one of the things that you can immediately say, is that like dissolves like. Nonpolar things will dissolve in other nonpolar things. So that means that oils and fats will mix happily together. What about water? Water is very, very polar, so it's only going to mix with other polar things. Examples of polar compounds are like sugar. Sugar is very polar. It's got these really, really highly electronegative oxygens on it, which make parts of the molecules very polar, and that means that you'll find that sugar dissolves very readily in water. In fact, you can mix them in almost any ratio to make like syrups and desserts. But here's the thing, is if you try and mix sugar in with oil, it remains undissolved because oil is nonpolar and sugar is polar. If you don't mix like with like, generally they will not mix. However, you can get some compounds which have got a polar piece and a non-polar piece, and that is why we use soap. Soap has got this polar part which talks to oxygen, and this non-polar part which talks to all of the fats and the lipids and the non-polar parts. Okay, so now let's take a look a little bit at how we're going to incorporate this into exam questions. Now, this requires a little bit of background. These are questions which I've taken from a DBE exam. So I'm not going to focus on this before we go to the ad break, but what I am going to do is lay the groundwork. It starts to talk about structural formulae, tertiary alcohols, and these isomers and whatnot. Before I do that, let's just decide how to decide these intermolecular forces. Now, there's three main categories when we're dealing with organic molecules. One is London forces. One is dipole-dipole. And then the last one is hydrogen bonding. Okay, so the reason that I've done them in this particular arrangement or in this particular order, and some of you might have actually called this London forces, sorry, temporary dipole. The reason that I've done them in this order is because they are in order of increasing strength. So that's going to become very important later on. So that is becoming stronger. Okay, so now how do I start to play around with what type of force we got? Well, here's the really nice thing, is if you've decided if your molecule is nonpolar, that means that you've got London forces between molecules. That is just a broad assumption, because London forces only happen when you're relying purely on accidental wobbles in the electron clouds. Dipole-dipole, all polar compounds will have dipole-dipole. Now, that's really nice. It's a really nice way of telling what type of intermolecular forces you've got. You will always have London forces on all molecules, but they are very, very weak. Dipole-dipole are slightly stronger, and only polar compounds can have those. Hydrogen bonding, well, you might have heard of NOF before, nitrogen, oxygen, and fluorine, plus hydrogen. Now, that's a little bit confusing. It means that if hydrogen is actually bonded onto nitrogen, oxygen, or fluorine, so if you've got NH or OH on your molecule, or HF itself, which is a bit weird because you can't actually bond anything else. But if you've got NH, OH anywhere on your molecule, that allows you to do hydrogen bonding. Now you might say, okay, well, why have we done this complete diversion? We're going to come back to this now. Let's read through our question before we take a break. Can you see that all organic questions start out with the microscopic and then work their way up to the macroscopic? Take a look at the trend. First, we start taking a look at hydrocarbons. Hydrocarbons, CH compounds, they start to take a look at saturated. Now we're looking at individual atom-atom bonds. Question 3.2, we're starting to take a look at, structural formulae. Functional groups. Now we can start to decide the polarity, and eventually we're going to work our way up to molecular properties. Tertiary alcohols, that's going to deal with the chemical properties again of an isomer of butane 1-ol. There's the alcohol. Now the really cool thing is, immediately, things like butanol, have got an OH group. That means that you will have hydrogen bonding. This thing is very likely to be a liquid or a solid if it's got hydrogen bonding, because hydrogen bonding is strong. These are the types of skills I want you to have before you even start answering these questions in your exam. I want you to take a look at which molecules you're dealing with. Are they nonpolar or polar? And remember, if they are nonpolar, London forces are the intermolecular forces. If they are polar, dipole-dipole. And further, you can have both of those and hydrogen bonding. It doesn't mean that you only have one type. It usually means that you talk about the strongest one that that molecule has. If it's got OH or NH, that means that it can also do hydrogen bonding, and that's the dominant one. That's the most important one that we talk about. If you've got hydrogen bonding, that means that molecules are going to stick very well together, and that means that it's going to take a lot of energy to break them apart, and I don't actually like saying that, separate them from each other, because the molecules themselves stay intact. That's one of the myths that I've heard. When you boil a molecule, it means that you are separating molecules from each other. You're not breaking up the molecule itself. It remains intact. If you boil water inside a kettle, you don't actually break it up into hydrogen and oxygen. All you're doing is you're separating out the water molecules from each other. And yeah, please, if you're making hydrogen and oxygen, your kettle is getting way too hot and you're about to blow up your house. So please don't do that. You need about 2000 degrees, so I don't think kettles do that. Okay, so let's get into answering this question a little bit after this break. I do want to take a look at a little bit ahead at the other questions which we're going to face. There's an investigation coming up a little bit later on, and I want you to try and see during the break if you can answer the questions. We've got learners investigating factors that influence the boiling points of alkanes and alcohols. In one of the investigations, they determine the boiling points of the first 3 alkanes. So that's methane, ethane, propane. Okay, how do I know those? Because they are anes. Anes means this part, alkanes is all C, single bond C. Okay, so methane, ethane, propane. You've got to find an investigative question. I want you to try to do that during the break. Fully explain why the boiling point increases from methane to propane. Take a look. We've gone microscopic. Now we're starting to take a look at the boiling point. So I want you to, when you go for the ad break and you're busy washing your hands and thinking about intermolecular forces, I want you to think about why a boiling point of something would increase. Why would it be more difficult and require more energy to be able to go from a liquid state into a gaseous state? Because that's what boiling is. I use energy to vibrate molecules, and eventually they vibrate so much that they can't stick to each other anymore. And that's when we've boiled our molecules off into the atmosphere. So when I've taken a liquid, changed it into a gas, I've either boiled or evaporated. Those are 2 slightly different concepts, but the effect is the same. I'm separating them by breaking the intermolecular forces, not the bonds inside the molecule. I want you to think about how we're going to do this investigative one. Okay, wash hands again, come back, rinse, repeat.